All right. So 1.2 is about science and engineering tools. Mainly, we kind of differentiate between the fields of science and engineering. And our essential question, which I know you guys don't have, you have to get it when we meet, is what are the similarities and differences between the fields of science and engineering? And this is the essential question you guys should be using at the end to write your summary. So your summary at the end should be just a 2 to 3 sentence summary of whatever we go in these notes. And throughout these notes, we are going to answer that question. So you can use examples as we move along. All right. What are the similarities and differences between the fields of science and engineering? So the work of scientists. Science is a field that helps us understand the natural world. Scientists will ask specific measurable questions that can be tested. That is the whole point of the scientific method. Remember, we make observations, we ask questions about those observations, and then we form a hypothesis. And that hypothesis has to be testable. And then measurable is best if we can actually measure it. We use the metric system. But we do use descriptions to measure too, especially when it comes to medical things. Usually there's a pain scale and a scale of 1 to 5. How much pain do you have? 1 being the least, 5 being the most. So they find a way to measure things that are otherwise hard to measure. Explanations and solutions. Scientists use observations and evidence to explain natural phenomena. Phenomena is just a big fancy word for some kind of an event that happens in the natural world. It could be any kind of event, an earthquake, the rituals of rhinoceros, anything can be considered a phenomena, just some kind of an event that scientists will look at and ask questions about. The information they collect during investigations is called data. Whether it's, like I said, actually measuring something or describing what is happening. Scientists use that data to build and improve explanations. So they go through that scientific method. They observe, they ask questions, form a hypothesis, test that hypothesis. They gather these results, put them into charts, and then the conclusion piece, they interpret those results. And ideally, that data will help them better explain whatever phenomenon they are looking at. That is the whole idea of science. So I believe all your blanks, there should be 4 blanks, and they're all bolded and underlined. The work of engineers. Scientists and engineers work very, very closely, but engineers use both science and math to solve problems or meet needs. So scientists come up with the ideas, engineers figure out how to make those ideas work in a logical, physical way. So engineers have to consider criteria. Criteria is what a successful solution must have or must do. If we want the successful solution to a problem, there are logical constraints we have to consider. Constraints are limits, such as cost, materials, or durability. So it's comparable to architects and engineers. So architects, if you don't know what an architect is, an architect will draw out a beautiful house for you. This is what we want the house to look like. This is what we want the kitchen to look like. Look at how pretty all of this is. Well, an engineer, a civil engineer, or a structural engineer will come in and use math to make sure that house is proportional and will stand upright and the walls won't blow down in the wind. So they can take that drawing, that dream from the architect and turn it into an actual reality where the house will actually stand and have 2 or 3 floors or whatever you want to build it as. They have to make those math calculations to bring it into reality. Models. Models are huge in both worlds. A model is a simplified representation of an object, system, process, or idea. Models can help explain how something works. They can make predictions, they can test ideas, and they can understand data. But they do have limitations because they cannot show every detail. So something like earthquakes. We can't purposefully cause an earthquake just so we can study what happens. So scientists have built models. There's mathematical models to simulate earthquakes on a computer system to see how it would affect the surrounding areas and the underground. Diseases is another one. You can't purposefully give people diseases just to study. Although that has happened. And in a couple of weeks, we're going to talk about scientific ethics. So scientists have built models. If we let this disease, they did it a lot for COVID. If we don't do anything about COVID, what's going to happen to the population? Planning investigations. Scientists conduct investigations to answer questions. Good investigations require careful planning, and scientists often use the steps of the scientific method, like I said, to guide their process. Once it gets to that experiment, scientists can make observations. They ask their questions about those observations. They make hypotheses and they design tests. When they design tests, sometimes those engineers get involved to make those tests an actual reality and take those logical steps. Analyzing and interpreting data. So after analyzing the results, scientists draw conclusions. They make changes if needed, and then they test again. We went over last week the example with the flashlights. You hypothesize that your flashlight, you make an observation, your flashlight's dead. You hypothesize that it needs new batteries. You run an experiment and you put new batteries in that flashlight. And if it works, great. Your hypothesis was supported. If it doesn't, you have to revise and go back. Okay, that didn't work. Let's see what else could be wrong. Maybe the light bulb in the flashlight is dead. Let's try that. That's just your next hypothesis. You test it again. And repeating investigations can make results more accurate and more reliable. The more you do something and the more those results stay the same, that's when you start to build a body of evidence towards a theory. And theory is the last step of the scientific method. And then
I think you froze.
it becomes an actual theory, tested over and over and over again, and the results are always the same.
You're back.
Okay, hear me now? Give me a thumbs up. Okay, thank you. It told me I lost my connection, so it reconnected by itself, which is good. Okay, we're almost done. And then communication is key. Scientists communicate information through writing, speaking, photographs, graphs, and other visuals. And then good scientists always cite their sources. You guys, I believe, are starting to practice that this week. Might have been last week, your scientific research. Either way, you always have to say where you get your sources from. Always have to make sure they're reliable sources. You should do that with any information that you get. Scientists have their own publications, their own journals that you can subscribe to and read about the work of other scientists. And they can look at an article from another scientist and how they did their work, how they followed the steps of the scientific method, and say, I want to do that again and see if I got the same results. And if they get the same results, like I said, it goes towards building that body of evidence. If they don't, then they get to figure out why. Why didn't I get those results? What was different between our experiments? Using evidence. Scientific arguments are based on evidence, not just opinions. If a scientist says something, it's because there's evidence behind it. Scientists will never say anything. They will never make a statement if they don't actually have the evidence to back it up. A claim should be supported with observations, measurements, or other evidence. Scientists evaluate and critique each other's ideas. Like I said, you read about another scientist's work and you're in that same field, I'm going to do that same experiment, see what kind of results I get. Scientific discussion can lead to better explanations and new discoveries. If we're always checks and balances, checking each other's work, okay, I'm going to do the same thing. Did you do it right? I got the same results. We do that more and more and more, those results become more and more reliable. And that is all for the notes. So write your summary on the last page. You don't have a box at the bottom. You can draw a box at the bottom, but it should be 2 to 3 sentences answering your essential